Hi everyone, we're going to take a look at the Arduino code today. So let's get started with it.
Okay, welcome everyone. Today we're going to take a look at the code for the self-balancing robot. As I've mentioned previously, the robot is based on a project by a guy called Dupe Broking, which I hope I've pronounced his name right. I'll provide a link to the initial project so you can go back and review that. And he also goes into quite a lot of depth with some of the code. I'm not going to go into as great a depth, but please feel free to go and have a look at his breakdown. In Dupe's project, he basically just provided all the code in line. I've taken a slightly different approach. I've broken out some of the major pieces to a couple of different classes, because I want to reuse this code in the self-balancing skateboard. So I thought it best to just break that code out now. So I've encapsulated the MPU code in a class of its own and also the PID code in a class of its own. So I might just start with that. PID is basically a control algorithm, and it's based on three terms: proportional, integral, and derivative. I'll do a separate video on PID in its entirety, I think, because it's fairly complicated. However, it's basically just a means of controlling a process variable to a set point. Okay, so we'll first cover off on the PID class. So essentially, if we look at the header file, there's a few public functions to reset the PID controller, set up the tuning parameters, set up deadband, some output limiting, and the actual calculate function. We've got some private parameters which are encapsulated within this class, and they're used to basically just store those parameters that are passed in. And then we have some public variables for set point, process variable, output, and also a self-balancing set point. So if we have a look at the actual code, so basically when the class is instantiated, we just reset the parameters to 0. We've got a reset function that can be called throughout the life of this class, which will just reset some of the variables back to 0. We've got the function here which basically just loads the PID parameters into those internal variables. Same with the deadband, and the same with the output limiting as well. However, with the output limiting, if there is a integral memory built up in the system, when we actually load in those new values, we actually constrain the output within those output min and max values. And then we have the PID calculate function, which is fairly straightforward. Basically, we just work out the error based on the process variable minus the set point. We've got a slight breaking function here, such that if the output is close to 0, then we modify the error just slightly. We accumulate the integral component here on each execution of the loop, and we also constrain it within min and max here. The output is the proportional term times the actual error plus the integral memory and added to the differential term, which is basically the change in the error since the loop last processed multiplied by the differential term. And then again we constrain the output within those limits. And here we save the error to the last error so that it can be used in the differential term calculation. We then apply some deadbanding. So basically, if the output is within a small amount of 0, then we just set the output to 0, and that just stops the system from hunting when the output is actually almost spot on the mark. Okay, so next we'll take a look at the MPU code. Okay, so the MPU code is for the gyro. And basically in the header file, we're just setting up some defines for the actual registers within the gyro and defining the radians to degrees, and then looking at the public functions. So the initializer, get the gyro calibration values, get the acceleration values, set the tilt angle, and get tilt angle. We've got some private values here. This acceleration calibration value is actually determined using a separate little bit of code that will calculate that value for you, and then it's basically just keyed in here, and it'll be different for every chip. And then we have some private functions that do the actual sort of real work. So if we take a look at the actual code, the MPU is communicated with over the I2C bus. So the first thing we do when we initialize the class or the instance is actually start the I2C communications and set the clock speed to 400 kilohertz. When we call the initialize, I did have this calling the reset function, and I found it seemed to be causing some issues, although I may have another look at that before I publish the code, because it may have been something to do with the serial communications just masking some funny goings on. So I may well uncomment that in the version that I publish. But basically then we just wake up the MPU, set the gyro full scale, set the accelerator full scale, and set the low pass filter. Maybe if we just scroll down and take a look at some of these functions, all we're doing is writing values to particular registers in the actual MPU. And you'll see that the method is fairly consistent. So basically we begin a transmission to the bus address. We declare which register we're going to write to, and these are these particular defines in the header file. And then we actually write out a value, and then we end the transmission. And basically that's how you actually set a register using the I2C bus. So reset is here, the wake up command here to this register, setting the full scale value. Basically all of these functions are here. I guess the only thing is where we're actually getting values, we set up the register that we want to read from, and then we actually do a request from the actual device with the number of bytes that we'd like to get. And here we're actually just converting the 2 bytes into a 16-bit word. And that's pretty much consistent for all of these reads as well. I will publish the data sheets for the MPU 6050. It's not that difficult to follow. I won't do a separate video, because if you go and follow on Dupe's videos, he goes into quite a lot of detail on the actual registers and everything like that. I have reviewed it myself, and look, it's not particularly difficult. The data sheets are quite easy to follow, and they're very, very comprehensive. Some of the maths takes a little bit of working through. However, as I say, it's not particularly difficult. You just need to persist with it, I guess. But anyway, all that's done and ready to go here. So now if we take a look at actual code, just scrolling down here, we've got some includes for those 2 classes. We set up the pins on the Arduino. For the battery low indicator, I'm just using the onboard LED on pin 13, and then we're setting up the pins for the motor drive. Setting the PID parameters here, they were just brought out here to make them nice and quick and easy to play with. Some dynamic parameters for the actual speed of the maximum speeds of the device and turn speed. Defines the states of the state engine. Some battery monitoring variables, Bluetooth communications variables. Loop timers. Report counter I don't think was used. The report counter I was using to to throttle the serial communications. And I actually found that you've got to be very careful with the serial communications, or you can overload the Arduino and it basically just stops and the robot falls over. So it's commented out at the moment, but I was dumping quite a lot of data out through the serial port to the phone, basically just for debugging purposes. Some control variables for the motor drive itself, and then we're actually instantiating the class instances for the MPU and the PID. Then moving into the setup, basically we're just starting up the serial communications, which on this device is via Bluetooth. Setting up the pin modes for they're basically all outputs. As far as controlling the stepper motors, we're actually using some timers and interrupts to do this rather than using pulse width or anything along those lines. Again, in Jupe's project, he goes into this in quite a lot of detail, and I would recommend going there. I'll publish the data sheet for the microcontroller. It's not rocket science. It's fairly easy to follow if you've had any experience with microcontrollers or microprocessors. However, have a look at the data sheet and follow along with his explanation. It is very good, and if I was to do it, I'd just be rehashing the same information. Set up the PID, give it a reset, load the parameters into it, initialize the MPU, turn on the waiting LED. I don't have a waiting LED on here, so we might just get rid of that because it does not exist. Okay, get the calibration values. So essentially this is happening while the device will be sitting on the ground, just waiting, just after power up. So basically so when you first power up the device, it'll be lying on the ground and it will just be sitting there collecting 500 values and then working at the average and storing them as calibration values. We then put the state engine into starting and set the loop timer or initialize the loop timer value. Okay, now stepping into the loop. If we've got any serial communications from Bluetooth, then we read the character in and just initialize a received counter. Basically, the received counter will reset the control from the phone back to basically nothing after 25 loops. So if for some reason communication fails or something like that, the app crashes or something along those lines, then the actual signal to speed up, slow down, turn left, turn right will actually just cease and the device will just come to a halt. We read in the battery voltage and we actually map it 0 to 1250. 1250 actually maps through to 12.5 volts. So basically we've got a couple of comparators here to check if the battery voltage is within 10.5 and 10.7. If it is, it'll send a warning over the serial port to the phone. If it gets underneath 10.5 volts but still greater than 8, so there is still a battery there, then it will actually set the LED on to indicate that there's a battery low voltage. It'll set the low battery variable to true, and it will actually print out over the serial port battery low. So we'll get that on the phone as well. Now that battery low variable will actually cause the device to stop. With the batteries we're using, you don't want to run them totally flat, so we basically just stop the device once the battery gets low. Okay. Moving into the next, or into the actual state engine itself, we'll enter here with the device starting, and you'll see here when it's starting, it will actually start reading the tilt angle, just using the accelerometer without any gyro input to start off with. And basically we'll sit in that state until the angle is within plus or minus half a degree of upright, whereupon it will set the tilt angle with the angle that it's got from the accelerometer, and it will move into the balancing state. So the next time through the loop, it'll be in the balancing state, and rather than getting the accelerometer angle, we start getting the tilt angle. Now the tilt angle is a combination of the gyro and the accelerometer, and this is what we use when we're in balancing mode. Now if the angle gets outside of plus or minus 30 degrees, or we get low battery, then the robot will drop back into starting and it will reset. So basically it's going to stop balancing. If those states aren't true, then we will actually calculate the output based on the process variable being the angle. Now we actually have a output variable that we can use to drive the actual wheels. So first of all, we set output left and output right to be the same as the output. If we have a signal from the Bluetooth communications, it will be either turn left, turn right, forward or reverse, and basically it will be equal to these particular values. Now, so if we want to turn left, we will actually add the turn speed to the left and subtract it from right, so that it will ask it to turn to the left. And the same with the opposite with turned right. Now with forward, we will actually reduce the set point by 0.05, and we will also take a look at the output to see how it compares to the maximum speed, and also just vary the set point according to that. And reverse is basically just the opposite of that as well. If we're not moving in forward or reverse, then we're going to tend to reduce the set point back to that 0 value. And if the set point is equal to 0 and the output is not equal to 0, we're going to tend to reduce the self-balancing set point as well. With the motor calculations, basically the stepper motors work in a non-linear function. Now PID loops work very well with linear characteristic control elements. So these calculations here are designed to make the stepper motor or speed control appear to be linear. So basically the output left and output right after these calculations will give us a control signal that we can apply to the stepper motors to control the speed in a linear fashion. Here we calculate the pulse times needed on the motors, left and right, and then we actually copy those values into the throttle control, and these will be used in the interrupt. I mentioned earlier that the report counter was here to throttle out the serial communications. As you can see, every 50th cycle it would actually print this data out. That caused all sorts of problems with the device locking up. I could probably throttle this further to probably quite a lot more loop cycles. However, it was really only used for debugging, so it's basically just commented out at the moment. And lastly, in the loop function, we have a delay of 4 milliseconds. So this whole loop is processed every 4 milliseconds. Okay, the interrupt handler. Okay, so essentially what we've got here is a couple of variables that are being incremented on every interrupt that's fired. And basically what we're doing is we're just counting up to the values that we've worked out from the code above. And once we get to that value, then we just reset the counter back to 0 and start again. Now, what we're doing in this block of code is we're checking to see whether the value is greater or less than 0 to determine whether we have to go forward or reverse. And we're directly setting the outputs by just ORing this binary value to the port for either forward or reverse here and here. Now, the other thing is, when the counter value is equal to 1, we're actually setting the pulse output high. When it gets to a value of 2, we're actually setting it low again. So that gives us a 20 millisecond pulse, and then this will continue to count until it gets to that variable that we worked out above, and then it'll get reset back to 0, and then it'll generate another pulse and count up again. So this is how we're controlling the pulses that are being sent to the motor driver. And we're basically just doing that for left and right here. And that's how the interrupt routines are used to actually generate the control signals for the motor. Okay, well look, there's a run through on the code, a very quick run through. Okay, well as I say, I'm getting very close to getting this up on the website. I'll do probably one more post just with some changes to the actual circuit, and I'll provide links to the code from there. Okay, thanks a lot.